Good morning. My name is Esteban García Cuesta, and I am Associate Professor at the Universidad Europea de Madrid. In the next, I'm gonna present my work that I have done with some of the researchers of my lab, which is entitled An Adaptive Cognitive Model to Integrate Machine Learning and Visual Streaming Data. This work is inside the area of cognitive artificial intelligence, where the main goal is to mimic human problem solving and to understand environment. For that purpose, the adaptability and the capability for generalize are key in order to obtain this purpose. Newell defined these capabilities to adapt the cognitive models as 5 of the 12 desirable criteria for artificial intelligence architectures. These 5, we have followed these 5 in order to make this work and to develop our work. So the first one is the flexible behavior of the cognitive AI. The second is the capability for doing real-time performance. The third is the adaptive behavior of the artificial intelligence. The fourth is the capability to get a vast knowledge base. And the fifth, is to have dynamic behavior in order to interact with the environment. On the applicability side, the model that we are developing and in the work that we have done in this work has a tremendous potential in the intelligent assistive technology area, because it can help to solve and to develop some innovative solutions in order to mitigate, for instance, dementia problems using home automatic sensors. These cognitive models can be used jointly with integration of machine learning methods to detect anomalous behaviors in these people that has dementia, or to predict future behaviors of these people. We also know that the use of raw machine learning methods by themselves doesn't allow to understand the scene properly or to maintain the real-time scene knowledge. For instance, whenever there is an object that hides another, if we don't have a proper knowledge cognitive model that represents the knowledge, then we will not be able to know exactly what is happening in the scene. So how do we represent this cognitive model? How do we represent knowledge? So basically, we have our input is going to be the webcam or the visual representation of the world. And then what we do is to transform this visual representation in numerical representation of objects and relations. And each one of these objects and relations are going to be stored in our knowledge base as a probability between 0 and 1. So we are going to create a knowledge base which is going to have beliefs, which are objects and relations, which has a probability of being true. Moreover, how this model treats these beliefs throughout the time is adaptive, because we represent these beliefs as a temporal series that has values between 0 and 1, and dynamically is going to be adapted by using the simple exponential smooth field method. So basically what we do is we are in real time analyzing what the visual information that we are getting from the environment, and then we obtain these new objects, these new beliefs about what is happening in the environment, and we are going to update in real time these beliefs by this formula. Here we have an object that is I is the object, W sub I is the belief, the probability that we believe in this object at the current time, T is the current time, delta T is the next time that we are going to do the analysis. And then in the right side, what we have is the update of this W sub I value, okay, which is basically the previous value multiplied by 1 minus 1 divided by the persistence parameter plus S sub I in T, which is the probability of detecting the object at time T. This is given by the detection of object algorithm and divided also by the persistency parameter. This persistency parameter basically measures the inertia of the model against any change, okay? And it depends of the object. It doesn't have to be the same for all the objects. It could be, but it doesn't have to be the same. For instance, if we know that an object has more inertia to be changed throughout the time than the other, then this parameter will be smaller. Okay. So the overall architecture basically is we have a sensor which is a now webcam sensor. What that we use for this work is sensing the wall. We get the information from the webcam. Then we apply the detection of the visual object detection algorithms. And then we have our cognitive model that I just explained, which is able to represent all the objects and relations which are in the scene, and also to update them and adapt to them in real time. And then we use machine learning in order to make predictions over the future or to detect anomalies. So in this case, we predict when in the future, in the time horizon age, when is going to be an object. So basically, what we did is to apply an LSTM deep neural network in order to predict when if an object is going to be in the scene in the future or not, if you believe it's going to be in the future or not. So we apply an horizon time in the future of 6 hours, and we use 6 previous hours in order to as input in the deep neural network. So this is the overall architecture. So basically we use the ReLU activation function. We use 128 neurons in the dense layer and also for the LSTM layer. And we use the sigmoidal function for the output, which means that it's going to be between 0 and 1. For the experimental design, what we did is we simulated an Alzheimer scenario, and we define a set of daily routines that the person will have. So we record 71 minutes, which are simulating basically 24 hours, and then we did this for seven days. The actions that we consider are eating, taking a medication, sleeping, watching TV, using objects, and some random actions or some random objects which were included in the scene. So this is the result of our cognitive model. So basically, our cognitive model represents objects and relations, as you can see. So the object table, for instance, so we have a detection probability, which is given by the visual detection algorithm. And then we have the cognitive model probability, which is the probability after has passed through our system. So this is what the cognitive AI has in its mind as a belief. Okay. The same for the fruit, and also the relations fruit table, the same. Okay. We also store the location of the objects. And then we use this deep neural network in order to predict the future. So we have some knowledge about what is happening every day, and then we wanted to predict, we wanted to test if we were able to predict what is going to happen tomorrow or after 6 hours in the future. Okay, and then we obtained very good results because we were able to integrate this in real time, obtaining like an R2 score of 98, or as you can see, a normalized root mean square error of 0.061%, which is basically a pretty good performance. So we were success with that. We also were success in applying this cognitive model in order to represent the scene properly without having or solving some of the problems as the hidden objects. Just to say that the persistence parameter that we use in this work was established to 10. And as conclusions, we can say that we have developed and tested an adaptable cognitive knowledge model integrated with machine learning algorithms. These architectures also can be useful in intelligent assistive technologies such as Alzheimer Home Assistant, and also other machine learning models are being tested, such as detection of anomalies. Thank you very much for listening, and I hope that you enjoyed the presentation. And here are my contact details, so if you want to ask me anything, you are very welcome to send me an email. Thank you very much.